a level not seen since 1936. On June 24th, a magnitude 5.6 earthquake struck near Ukiah, British Columbia, the largest rupture ever recorded on the Maacama fault system in modern instrument history. Exactly 34 days later, the same fault moved again. At 7:40 p.m. Pacific Time, 55 kilometers to the south-southeast, a magnitude 4.3 earthquake broke the shallow, brittle crust beneath Sonoma County. Within hours, the United States Geological Survey logged more than 160 associated seismic events. It did not classify the rupture as an isolated bump. It flagged it explicitly as a potential mainshock. That single word, potential, carries the entire unresolved uncertainty of modern Earth science. This isn't just a California story, it's a continental strain story. The Maacama carries a massive share of the North American Pacific Plate boundary motion, the same tectonic forces that drive our own silent threat, the Cascadia Subduction Zone off Vancouver Island. This fault runs straight toward the Rodgers Creek and Hayward fault network, heading directly into the most densely populated corridor of the Pacific Rim, and its buried record holds ruptures far larger than anything in the modern catalog. Headlines called it a minor tremor in a busy week that saw a magnitude 6.8 strike Kumamoto, Japan. But that framing misses the actual mechanics. The title sells the local drama, but here is the accurate version, and why it is the far better story. This isn't about one small quake shaking dishes in a kitchen. It's about a high-productivity sequence on a fault that bleeds off only part of its motion through slow creep, while silently accumulating the rest as elastic strain. The tension in this system comes from precise physical reality, not exaggerated adjectives. At 5.5 kilometers depth, this rupture occurred in the upper crust where shaking reaches maximum efficiency for the energy released. When a single patch breaks and settles, you get a dozen aftershocks. When a sequence population reaches into the hundreds across hours, it means a broad volume of the Earth's crust is sitting near its critical breaking point and actively reorganizing itself. Over the next few minutes, we will explain the physical mechanism behind foreshocks, how slow fault creep acts as an incomplete safety valve, and why early warning systems hit a hard wall of physics in the epicentral zone. But above all, this episode answers one single critical question. When a fault that hasn't produced a major cataloged rupture in nearly 9 decades moves twice in 5 weeks, are we watching a routine release of local stress, or the step-by-step loading of a much larger continental disaster? To grasp why this sequence is resetting scientific baselines, you have to look at how this fault system was measured before the summer of 2024. For nearly 9 decades, the Maacama fault system in Northern California was treated as a secondary player in North American strike-slip mechanics. Running parallel to the San Andreas through the Coast Ranges, the Maacama dips between 50 and 70 degrees to the east. Modern deformation models, including the 2023 National Seismic Hazard Model, built by the United States Geological Survey, established its average slip rate at roughly 9 millimeters per year, give or take 1.5 millimeters. To put that in perspective, the offshore San Andreas carries roughly 24 millimeters a year, the highest rate on the regional grid, yet that offshore section has produced almost no cataloged earthquakes in modern history. For generations, the public and local planners viewed the Maacama through the comfortable lens of fault creep. Creep is slow, continuous movement where tectonic blocks slide past one another without generating violent shaking. On the Maacama, instruments measure this creep at between 2 and 6 millimeters per year. You can see it physically in towns like Willits and Ukiah, where concrete curbs, utility lines, and road alignments are offset sideways over time. The popular narrative framed this creep as a safety valve, a continuous release mechanism that bleeds off tectonic energy before it can trigger catastrophic ruptures. That framing was fatally incomplete. The basic arithmetic proves why. If the plate boundary forces push this zone at 9 millimeters every year, and surface creep accounts for only 2 to 6 millimeters, then between 3 and 7 millimeters of displacement is withheld every single year. That deficit does not vanish. It stores itself inside the rock mass as elastic strain, waiting for a threshold to break. The historical baseline appeared tranquil only because the instrumental catalog is brief. On the morning of June 24th at 10 minutes past 8 local time, that tranquil baseline collapsed. A magnitude 5.6 earthquake struck near Ukiah in Mendocino County, centered beneath a remote monastery in the forest. Seismometers within 10 kilometers recorded severe ground shaking at intensities between 6 and 8 on the modified Mercalli scale. USGS models estimated that 10,000 people experienced intensity 7 shaking, cutting power to thousands of homes and generating over 4,500 felt reports. The focal mechanism aligned perfectly with the Maacama, a strike-slip plane dipping 54 degrees to the northeast. That June event was the largest earthquake ever recorded on the Maacama Fault in the entire history of the USGS catalog. It broke a nearly century-long quiet period along that specific trend. Then, just 34 days later, the magnitude 4.3 sequence struck near Cloverdale, 55 kilometers to the south-southeast. Two significant events in 5 weeks along a single structure that had never produced an event above magnitude 5.6 in the modern record. Furthermore, paleoseismic trenching near Willits revealed that the ancient record contradicts the short modern catalog. Careful sediment excavations uncovered offset soil layers pointing to multiple ruptures between magnitude 6.5 and 7.0 or larger within the last 1,200 years. Because small earthquakes do not leave permanent physical scarps in the geological sediment, those ancient layers prove that this system regularly produces massive ruptures. A magnitude 6.6 releases roughly 30 times the energy of the June magnitude 5.6 event. The historical baseline didn't prove the Maacama was safe. It only proved that our human instruments arrived during a brief, quiet interlude between major cycles. At 5.5 seconds after the rupture began on June 24th, the automated sensors of Shake Alert registered the first P wave. In 5.5 seconds, seismic energy moving through crustal rock travels roughly 18 kilometers. By the time 657,000 push notifications were dispatched through the MyShake application across the region, the people standing directly in the area of strongest shaking had already been hit by the S-waves. This was not a failure of technology or network speeds. It is a fundamental constraint of physics. Public early warning infrastructure, whether Shake Alert along the Pacific coast or Public Safety Canada's Alert Ready system, cannot predict earthquakes. They detect them. An earthquake must physically break the rock before any instrument can transmit a signal. Because radio signals travel at light speed while seismic shear waves travel at roughly 3.5 kilometers per second, warning times increase the farther you are from the epicenter. For San Francisco or Vancouver, 30 seconds of warning is genuinely life-saving. For the neighborhood sitting directly above the epicenter, the physics cannot be beaten. The blind zone is absolute. The failure of public perception regarding early warnings is only the first layer of the problem. While tracking seismicity between the Maacama and Bartlett Springs faults, researchers identified an unmapped anomaly in the Northern California coast ranges. Catalog data revealed a prominent linear alignment of recent earthquakes, a clear structural signature of an active fault. Yet, when cross-referenced against the National Quaternary Fault and Fold database, the authoritative United States inventory of active faults, the structure was missing. Mapping by the California Geological Survey classified structures in that zone as pre-quaternary, meaning inactive for over 2.6 million years. Seismologists reviewing the public catalog had to crowdsource its identity, eventually referencing a 2013 paper in the journal Geology to confirm the feature. A major, seismically active structure capable of transferring strain had gone unclassified in official databases. To understand the core mechanism driving this entire system, you have to look at how stress transfers between connected faults. Moving southeast along the Maacama trend, the structure links into the Rodgers Creek Fault, which runs straight through Santa Rosa toward San Pablo Bay. For decades, geophysicists debated whether the Rodgers Creek Fault ended at the bay or connected to the Hayward Fault beneath the water. In 2016, direct subsurface imaging published in Science Advances proved they are physically joined, a single continuous 190-kilometer structure bending 10 degrees across the bay. The maximum modeled magnitude for a full-length rupture along this combined Hayward-Rodgers Creek structure is magnitude 7.4, releasing roughly 700 times the energy of the June earthquake near Ukiah. While a magnitude 4.3 near Cloverdale does not directly load the Hayward Fault through causal domino effects, it demonstrates that stress is actively reorganizing on the northern gateway of a continuous system that terminates in the most densely populated urban corridor in Northern California. Near the Geysers geothermal field, the largest electricity-producing geothermal complex in the world, shallow, induced micro-earthquakes occur routinely due to steam extraction and fluid injection. But those events are localized inside the geothermal reservoir volume. The Cloverdale sequence and the June rupture occurred tens of kilometers outside that field, on a deep, brittle tectonic boundary moving under unreleased strain. 3 separate events across a hemisphere that turn out to be 3 readings of a single number. Within the exact same 48-hour window that Sonoma County moved, 2 other major plate boundaries flared across the Pacific Rim. On Tuesday afternoon at 4:30 Japan time, a shallow magnitude 6.8 rupture struck Kumamoto Prefecture on Kyushu. It registered Shindo 7, the absolute maximum intensity value on the Japanese seismic scale, a level reached only a handful of times in modern history, including the Noto Peninsula quake in January 2024. Sections of the Kyushu Expressway split open, historical stone walls at Kumamoto Castle collapsed, and fires broke out across Kumamoto City. At a commercial shopping complex, part of the second floor collapsed before a massive gas explosion tore through the structural frame, leaving dozens missing and wounded. Simultaneously, along the Tonga-Kermadec Subduction Zone, the fastest converging plate boundary on Earth, moving at up to 24 centimeters per year, a dense, spatially extended cluster of over 30 earthquakes above magnitude 4 and 5 fired across 36 hours. Yet, statistical physics proves these events did not trigger one another across oceanic distances. Static stress changes decay within 2 rupture lengths, and dynamic seismic waves passing through the crust trigger secondary events almost exclusively within minutes or hours in pressurized geothermal reservoirs, not 12 hours later on a distant strike-slip fault.
They are independent readings on a single global machine.
And that independence is the far more concerning reality. California is moving on its own internal clock. To see what happens when sequence classifications go wrong, look back at Kumamoto in April 2016. On April 14th, a magnitude 6.5 event hit the Futagawa and Hinagu fault zones. It was designated as the mainshock. Emergency services deployed, residents returned to inspect damaged homes, and life resumed. 28 hours later, a magnitude 7.3 struck the exact same fault trend. The initial magnitude 6.5 was reclassified as a foreshock only after the larger disaster arrived. This is why the USGS's precise language on the Cloverdale event carries immense weight. Statistically, after any given rupture, there is a 6% chance a larger event follows within 3 days, and a 5% chance within a week. That means 19 times out of 20, a magnitude 4.3 is the main shock. But the 5% case cannot be identified in advance by any monitoring station or algorithm. The danger lies in the reality that foreshocks look physically identical to ordinary earthquakes at the moment the rock snaps. For residents and infrastructure operators along the North American West Coast, the real-world impact is immediate. If a cascade migrates south toward Santa Rosa or east toward buried urban fault intersections, critical transit corridors, regional power grids, and water conveyance pipelines cross these fault traces directly. In a major rupture along the Hayward-Rodgers Creek structure, modeling shows severe structural disruption across key supply networks. The difference between a quiet cluster and an escalating sequence isn't an abstract geological debate. It is the direct metric that determines whether emergency response teams are standing by or caught off guard. Here is what we know for certain, and the exact boundary where established science ends. We know the Maacama fault system moved twice in 5 weeks. First on June 24th with a magnitude 5.6 near Ukiah, the largest earthquake on record for that fault, and then on July 30th with a magnitude 4.3 sequence near Cloverdale, accompanied by more than 160 associated seismic events. We know that the Maacama slips at roughly 9 millimeters per year, while surface creep accounts for only 2 to 6 millimeters, meaning residual elastic strain is constantly accumulating in the rock mass. We know from paleoseismic sediment studies near Willits that this structure has produced ruptures between magnitude 6.5 and 7.0 within the last 1,200 years. And we know that tectonic tremor monitoring along the southern Cascadia Subduction Zone off Vancouver Island returned 0 events on Tuesday evening, confirming that the megathrust boundary to the north is not currently responding to this activity. What remains unresolved is whether the 160 events near Cloverdale represent the quiet decay of a minor sequence or the early foreshock signature of a larger rupture. Science cannot make that call in advance. The classification of a mainshock is available only in hindsight. Until one of two specific developments occurs, the most likely situation is that this sequence will decay quietly over the next week, consistent with standard 95% aftershock probabilities. Here are the 3 checkable items to watch over the coming days. First, check the spatial distribution of the aftershock map. If the epicenters remain tightly clustered around the initial hypocenter near Cloverdale, the sequence is settling. If the events elongate along the fault trend, migrating northwest toward the June rupture near Ukiah or southeast toward the Rodgers Creek fault, it indicates active stress transfer onto adjacent segments. Second, monitor the USGS automated forecast feed for the Cloverdale sequence. The agency's model expects at least one aftershock of magnitude 3.0 or greater within the 7-day window following Tuesday. Where that specific magnitude 3 event lands will reveal whether stress is concentrating or dispersing. Third, watch for any formal seismic advisories issued by the United States Geological Survey for Northern California, or corresponding monitoring updates from Natural Resources Canada and the Geological Survey of Canada regarding regional strain transfer along the Pacific Rim. What changed this week was not the tectonic loading. The plates never stopped moving. What changed is that a fault running straight toward the Bay Area, storing far more strain than its surface creep suggests, just reminded us that the instrumental catalog is far shorter than the Earth's memory. Let us know in the comments where you are watching from today. Subscribe to stay informed as we continue to track these developing geological systems.